Hey there folks, in this video I wanted to go through a few practice problems using capacitors and Kirchhoff's loop injunction rules and how you might use those to answer multiple choice questions. For each of these I encourage you to pause the video, try the question on your own first, and after you've given it a real earnest attempt, then move forward with the video to see my explanation. Here's the first question. In the circuit shown above, the switch S is open and the capacitor is uncharged, and the current through the battery is ½ amp. We want to know what the charge on a capacitor is a long time after the switch is closed. And my hint here is that color coding equipotential wires helps a lot. So take some time to give this a go, pause the video, and then I'll reveal the answer in 3, 2, 1. Alright, so let's go ahead and talk about the solution. I have the circuit redrawn here. I'm going to do some color coding with this circuit. So let's go ahead and do that. The top part of this will all be red. That switch S is closed. All of those are connected to the top end of the battery. The bottom end of the battery, I'll go ahead and color code that in purple. And I will use a gold color to connect or to mention that all of the wires that are connected there at the bottom are at the same potential value. Now, the key word here is that the switch has been closed for a long time, which means that the capacitor is charged enough to prevent any current flow down the branch with the capacitor. And so, there is no flow of charge through the middle resistor, which means that the difference in potential across that resistor must be 0. So both ends of that resistor are at the gold potential level, so that the difference in potential is 0. So our end goal is going to be to find the delta V across the capacitor, but we'll notice that we have red and gold here. I can use this resistor over here to find the difference between red and gold to then find the delta V across the capacitor. So I can use the other branch to figure out something about the capacitor branch. And since there is no current flow here, I know that this ½ amp, all of it goes to the 10 ohm resistor. So, if we take and look at this rightmost resistor, the ½ amp times 10 ohms, we know that the delta V, the difference in potential across the resistor, is 5 volts. That means that the capacitor, which has the same difference in potential, must also have a 5 volt potential difference. Using the definition of capacitance and rearranging it to solve for charge, we can see that 5 times 10 to the minus 6 farads times 5 volts gets you a 25 microcoulomb charge on one of the plates of the capacitor a long time after the switch has been closed. So the key idea when these are closed, and they've been closed for a long time, is that the capacitor branch blocks current, and you can usually use another parallel branch to help you figure out the delta V from the capacitor if you do the color coding to help you out. So that's the key idea there. The circuit shown above has been connected for a long time. What is the charge on one plate of the capacitor? Take a moment to give it a go. Revealing answers in 3, 2, 1. So first, the words long time are the clue here. We're in a steady state, which means that the capacitor has been charged enough to where it's blocking any current flow through this branch. This branch essentially has no current flow. So let's do our color coding. I'm going to choose to color code it like this, where the top of this battery is purple. All of these connected wires are red. All of these connected wires are blue. And then because there is no charge flow through this middle branch, the potential value on either side of this 6 kilo ohm resistor must be the same because the delta V and the I are 0. There is no difference in potential across the 6 kilo ohm resistor. So now we can go ahead and look at this 6 kilo ohm resistor and say, all right, we know this resistance, we know this current, we can find out the potential difference between red and blue. So take your 2.25 milliamps times your 6 kilo ohms, you end up at 13.5 volts. So the difference between red and blue is 13.5 volts. But oh look, the capacitor in question also is the same difference between red and blue. And so again, using our definition of capacitance, we take the capacitance times the potential difference, and you find the value for the charge. And that value is, I can't see, hold on, give me a second, 27 microcoulombs. So that is option C. Third example. In the circuit above, the current through the battery is 15 amps. Which of the following correctly describes the current I into and out of point P? So, this I1 is what they're saying. Oh, hold on. Think about it first. Giving answer in 3, 2, 1. Okay, I1 they're saying is 15 amps. There's 15 amps of current coming out of the battery. And so at point P, there must be 15 amps going in. I1 is 15 amps. These are all 2 ohm resistors, so that 15 amps will split evenly across these 3 branches. And so what we're left with is I2, I3, and I4 are all 5 amps, which is option C. So there's an analysis of some more complex circuits. I hope that was helpful. Please let me know what questions you have.